Hello everyone, welcome to the video lecture on refrigeration cycle. Today we are going to talk about the gas refrigeration cycle. So in the previous chapter we talked about the Brayton cycle, which is basically a gas powered cycle. Uh, let's take a look on the Brayton power cycle and then we'll come back again on the gas refrigeration cycle. Okay, so in the Brayton cycle, the key component are like this. So we had a compressor, and then that compressor was connected to a turbine, right? From the compressor we had a combustion chamber, and from there it was connected to the turbine. So that was basically the simple Brayton cycle. So this is the inlet and then outlet of combustion chamber and outlet of the turbine. Okay, and that turbine is producing some sort of work, W turbine, and this compressor was consuming some work, right? So WC, this is combustion chamber. What is happening here? Here basically, this compressor is compressing the gas and increasing the temperature and pressure, right? So 1 2, and then this is 3 and this is 4, right? So here it's basically 1 to 2, pressure and temperature is increasing due to the compressor, right? And then that compressed gas, it's basically combusting into the combustion chamber, thus producing the high temperature as well as high pressure. And then when it's expanding through this turbine, it's producing the work, WT amount of work, and it becomes like atmospheric temperature and pressure. It's exhausting that compressed gas in atmospheric temperature and pressure. So basically the expansion process is happening in the turbine and temperature and pressure is reducing, right? What if we take this similar concept in the refrigeration cycle but in the reverse way? How is it possible? Let's take a look. So if we have, for example, a turbine, and then that turbine is connected to a compressor, right? So basically, and then there is a heat exchanger. Okay, so this turbine, and then basically this inlet here will be my cold space. Okay, and from here it will be going to the compressor inlet. So this is inlet, this is outlet, and this is the turbine outlet, and it's coming to the. Now let's take a look what is happening here. So if we consider this point 1, and then this is 2, and then this is 3, and this is 4. So here this compressor, it's basically it's consuming some work, right? WC or W net in, right? Input, right? So this compressor is basically compressing the gas, and that gas it's passing through a heat exchanger. What is this heat exchanger is doing? So heat exchanger is basically placed in outside, right? So basically it's rejecting the heat, QH amount of heat, it's rejecting the heat in this heat exchanger. And then that however the pressure is still, because it's constant pressure heat rejection, however the pressure is still high, right? So when we expand that high pressure gas through a turbine, then what is happening here, it's also reducing the it's also reducing the pressure and temperature. So now it becomes at point 4, it's really cold temperature, low temperature gas, right? So when we pass that low temperature gas through a cold space, right, what is happening here, it's basically absorbing the heat from this source, and then that heat is QL, absorbing the heat from this space and making this space as I mean making this refrigerated or conditioned space low temperature, right? So when it's this vapor, it's basically this gas, it's basically taking the heat QL from this cold space, it becoming the vapor again it's going through this compressor and producing this continuing this cycle. So it is very similar to the Brayton cycle, however it is a reverse type, right? So basically you can see that I mean in this configuration, combustion chamber, instead of combustion chamber we are using a heat exchanger where it's rejecting the heat. However, here in the combustion chamber it is adding the heat, right? Heat addition is happening in combustion chamber, however in heat exchanger heat rejection is happening. So gas refrigeration cycle is nothing but, so gas refrigeration cycle is a reversed Brayton cycle, right? Now question is that instead of expansion valve, or instead of the turbine, can we use the throttling valve, right? You have to answer this question, can we use the throttling valve on this cycle, right, instead of turbine? Can we use the throttling valve right here instead of this turbine, and what would be the difference, right? So basically that's the basic working principle of the gas power refrigeration cycle or the gas refrigeration cycle. Let's take a look at the by the way, this is, I would like to ask you all that instead of gas turbine, instead of the turbine, can we use the throttling valve in this cycle to run this gas refrigeration cycle? Let's see what is the answer. And then excuse me, then TS diagram of this cycle will look like this. So heat addition, basically let's take a look where from 2 to 3 or 1 to 2 is the compressor, right? So this is 1 to 2 isentropic TS diagram. So 1 to 2 is compressor, isentropic compression, temperature and pressure is increasing, and 2 to 3 is basically constant pressure line, right? Constant pressure heat rejection, 2 to 3. And then 3 to 4 right here, 3 to 4 it's basically expansion, right? Isentropic expansion, and temperature is falling down here as well. So 3 to 4, and then 4 to 1 again the heat absorption. So this is the QH heat rejection, and this is the QL heat absorption, okay? QL heat absorption. And then we have to work consume, right? The work consumption, WC, or the compressor work right here. And then if the turbine is producing the work, then it will be WT here as well. So, and if we instead if we use the throttling valve, then it will not gonna produce the work, or we don't have to put here. Okay, so basically there is the TS diagram. So just by looking at this TS diagram, what are the things we are looking at it. So again, let me consider this is we are using the turbine, right? So the turbine is producing some work, WT. So if we do the analysis of coefficient of performance of this gas refrigeration cycle, then coefficient of performance of gas refrigeration cycle, it's basically QL divided by W net. Okay, so what is the QL? So the QL, it's basically here, it's H1 minus H4, right? So QL equals to H1 minus H4. And then what is the W net? W net is nothing but compressor minus the turbine, right? So W compressor input minus W turbine output. Okay, so we know that W compressor input is happening in between H2 minus H1, and W turbine output is H3 minus H4. Okay, so if we just plug in this value, then COP of gas refrigeration cycle, GRC, would be H1 minus H4 divided by H2 minus H1 minus H1 minus H4. Excuse me. The turbine output, right? So H3 minus H4. So it will be H3 minus H4. Okay. So that's the expression of the coefficient of gas refrigeration cycle. Now, although the gas refrigeration cycle has very low COP in real application, however, it has two desirable characteristics, right? So two desirable characteristics. So what are these two desirable characteristics? First of all, they are simple and lighter components, which make them suitable for aircraft cooling application. In the previous class, we were talking about the aircraft cooling mechanism. You know how liquid nitrogen cools down the aircraft. So this reversed Brayton cycle or gas refrigeration cycle is mostly used for aircraft cooling application, right? So that aircraft cooling application is basically the open cycle aircraft cooling system. So if we draw the open cycle aircraft cooling system, it will look like this. So basically we have a turbine, all right. That turbine is connected to a compressor. Okay, and then we have a heat exchanger, right? So here, and this is output. So it's an open cycle aircraft cooling system. Open cycle aircraft cooling system. Okay, so this is the turbine producing the this is the compressor basically consuming some work, WC, and this turbine is producing some work, WT. Excuse me. Okay, so Right, so that's the schematic diagram of 1 to 2, and this is 3 2 to 3, and this is 3 to 4. That's the schematic diagram of open cycle aircraft cooling system. And it's a open cycle aircraft cooling system. However, to make it more efficient, we can use the regenerative type gas cycle for the same application, or basically the aircraft cooling application, or a lot of cryogenic application. So another thing is about the um, so this is one thing, a simple and lighter component which makes them suitable for aircraft. And then two, open system allows the low temperature fresh air to be circulated in the cabin space. And so basically you take this number 4 as it's your cabin space, right? um, so that's the benefit of this. It is simpler, lighter, and there is no such complex instrumentation. That's why we use it in aircraft cooling application, or a lot of cryogenic application as well. However, to make it more efficient, right, to increase the efficiency of this type of cycle, we saw that we did regeneration. We also, if it is vapor involved, then we did cogeneration, reheat, right? However, for this one gas power cycle, we can do the regeneration. How the regeneration we can implement, let's take a look. So basically you have a turbine, and then from that turbine it's connected to a compressor, right? So compressor outlet, compressor input is right here, and then compressor output is right here. So that compressor output is going to a combustion chamber for heat exchanger first. Okay, so from that heat exchanger we can take that exhaust or output to a regeneration unit. So in this regeneration unit, it will leave some, or it will reject some heat, right? H, it will reject some heat, and then it will become low temperature, still high pressure, and then that high pressure vapor will be, or gas will be expanded through this turbine, and then outlet of this turbine, it's going through this regenerator unit. Basically it is absorbing the heat now, okay, which is it is absorbing the heat. Okay, so before that we can pass that one through a uh, like the conditioned space, conditioned or refrigerated space, refrigerated space. Okay, so here it is basically absorbing the heat, okay, QL amount of heat it is absorbing, and then becoming vapor again. It is also absorbing some sort of heat right here, QL, right? QL prime, let's say QL prime, and then excuse me, and then it's becoming the vapor again, and then that vapor is coming as the input of this compressor, right? So if we mark these points, then it will be number 1, it will be number 2, it will be number 3, and it will be 4, and then 5, and then this is 6, and this is 7. So here the key thing is this regenerator unit, right? So the amount of heat rejected by this 3 to 4 process equals to amount of heat gained by 6 to 7 process, right? So QH and QL prime, it's basically the same. So this is the regenerator system. This is compressor excuse me, this is turbine, okay, and this compressor is basically consuming some work, and this is producing some work, right? WC and WT. So that's the regeneration system or regenerator unit. regenerative gas refrigeration cycle. Okay, so this is much more efficient than the open cycle one, right? We are circulating the same air and getting the more cooling effect. And also if we look at the TS diagram, we'll see that the 1 to 2 it's basically the compressor, and then 2 to 3 is the heat rejection, right? And then from 3 to 4 the same, maintaining the same pressure, constant pressure line, right? 3 to 4 it's basically right here, it's rejecting the heat, so that the temperature is decreasing. And then 4 to 5 it's expansion, and then again 5 to 6 is the heat addition. Oh, right. So here it's absorbing the heat QL, and then QH, and then from 6 excuse me 6 to 1 it's basically here, right here, 6 to 1, or actually here there is no point to make it 7, so it's the same, 6 to 1. Okay, so basically here it will be 6 to 1, and in 6 to 1 this QH and QL prime is the same, so it is absorbing QL prime. Okay, so this is the S and this is the T. So now we know that where is the heat addition and heat rejection is happening, and then where is the WC and where is the WT. We can simply calculate the COP for this cycle as well. So that's all about the gas refrigeration cycle.